Graphene, a single layer of carbon atoms arranged in a hexagonal honeycomb lattice, has captivated scientists and engineers since it was first isolated in 2004. Though it is just one atom thick, graphene displays a set of properties that seem almost too good to be true. How can something so thin be stronger than steel, more conductive than copper, and nearly transparent? Let's explore what makes graphene so unique and why it has sparked a revolution in material science. To begin with, graphene is exceptionally strong. Despite its thinness, it is about 100 times stronger than the strongest steel. This strength comes from the carbon-carbon bonds that form its structure, the same bonds found in diamonds. However, unlike diamonds, graphene is also flexible and stretchable, allowing it to bend without breaking. Imagine a material you can roll, fold, and stretch, yet it still holds together with incredible strength. Graphene is also an excellent conductor of electricity. Electrons move through graphene with very little resistance, almost like they are moving at the speed of light. This is due to a peculiar behavior known as ballistic transport, where electrons can travel long distances without scattering. This makes graphene ideal for ultra-fast transistors, next-generation computer chips, and sensitive biosensors. What about heat? Graphene is among the best thermal conductors known, meaning it can dissipate heat rapidly. This makes it useful in applications like cooling systems for electronics, LEDs, and solar panels where managing heat is a constant challenge. Interestingly, graphene is almost completely transparent, absorbing just 2.3% of visible light. This opens the door for its use in transparent touchscreens, smart windows, and solar cells that capture light without compromising visibility. Can you imagine a phone screen that is almost indestructible, paper-thin, and conducts electricity better than metal? Another property is impermeability. Even helium, the smallest gas atom, cannot pass through a sheet of graphene. This makes it a great candidate for gas separation, membranes, water purification systems, and even protective coatings to block corrosion or oxygen damage. In medicine, graphene is being explored for drug delivery, tissue engineering, and even neural interfaces. Its biocompatibility and high surface area make it suitable for carrying drugs directly to targeted cells. In one experiment, researchers loaded anti-cancer drugs onto graphene sheets and guided them to tumors using magnetic fields. Could this become the basis for personalized, non-invasive treatments in the future? However, graphene's real power might lie in its combinations with other materials. Scientists are developing graphene-based composites that enhance the properties of plastics, metals, and ceramics. For example, adding even a tiny amount of graphene to concrete can increase its strength and durability. In batteries, it improves the efficiency and speed of charging. Graphene-enhanced lithium-ion batteries could charge your phone in minutes and last much longer than today's models. But if graphene is so amazing, why isn't it everywhere already? One of the biggest challenges is scaling up production. While we can produce small quantities of high-quality graphene in the lab, making it on an industrial scale at low cost is still difficult. Methods like chemical vapor deposition, exfoliation are being refined, but large-scale integration into commercial devices remains a work in progress. Graphene also poses new engineering and ethical questions. How do we dispose of it safely? Can it interact with biological tissues in unexpected ways? How do we prevent monopolization of such a powerful material? Despite these challenges, the graphene revolution is underway. Governments and industries are investing heavily in research and development. From energy storage and sensors to wearable electronics and water filters, graphene is finding its way into real-world applications. Is graphene the wonder material of the 21st century? Possibly. Its unmatched combination of strength, conductivity, flexibility, and transparency makes it unlike any other material we know. The more we explore it, the more possibilities we uncover, not just for new technologies, but for rethinking how materials behave at the atomic level. Graphene is a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, giving it a unique combination of dimensional simplicity and atomic robustness. Its EF2 hybridization creates strong covalent bonds in plane, while delocalized p electrons confer remarkable electronic and thermal properties. The absence of defects and minimal thickness 0.34 nm X-rays and an exceptionally high surface area to mass ratio. These foundational characteristics underpin graphene's multifunctionality across physics, chemistry, and engineering. Monolayer graphene, grown by chemical vapor deposition, serves as a pristine platform for high-speed transistors. Graphene is like a single sheet of chicken wire at the atomic scale, ultra-thin, yet extraordinarily strong. Despite its one-atom thickness, graphene exhibits a tensile strength of ~130 GPa, over 100 times stronger than structural steel of equivalent weight. Its Young's modulus of ~1 TPa reflects extreme stiffness, resisting deformation under high stress. This combination of strength and flexibility arises from the robust carbon-carbon bonds in its planar lattice. Consequently, graphene can endure large strains greater than 20% without fracture, making it ideal for reinforcement applications. Incorporating graphene into polymer composites increases material strength and toughness for aerospace components. Graphene is like a microscopic Kevlar sheet, featherweight yet tougher than steel. Graphene's delocalized p electrons move freely with minimal scattering, yielding room temperature electron mobilities exceeding 200,000 bm2/vs. Its zero-band gap, semi-metal nature allows electrons to behave as massless Dirac fermions, resulting in ballistic transport over micron distances. This translates into ultra-fast charge carrier speeds, enabling potential transistor switching frequencies in the terahertz regime. Graphene's conductivity outperforms copper by weight, opening avenues for lightweight, high-frequency electronics. Graphene-based field effect transistors operate at gigahertz speeds with low power consumption. Graphene is like a superhighway for electrons, smooth, wide lanes that let traffic flow at top speed without congestion. Graphene conducts heat at rates of ~5000 W/mkk, several times higher than diamond, due to efficient phonon transport across its two-dimensional lattice. This property allows graphene to rapidly dissipate localized hotspots in electronic devices, improving reliability and performance. The high thermal conductivity persists even in ultra-thin films, making graphene ideal for thermal interface materials. Integrating graphene into heat sinks and spreaders mitigates overheating in compact electronics. Embedding graphene sheets in smartphone casings significantly lowers internal operating temperatures. Graphene is like a nanoscale heat pipe, quickly wicking away thermal energy wherever it concentrates. A single graphene layer absorbs only ~2.3% of visible light despite being atomically thin, granting it ~97.7% transparency. This combination of transparency and conductivity is rare, enabling graphene to function as a transparent electrode. Unlike brittle metal oxides, graphene electrodes remain flexible and robust under mechanical deformation. These traits make graphene ideal for next-generation flexible displays, touchscreens, and photovoltaic cells. Graphene-coated windows serve as transparent heaters and touch-sensitive displays. Graphene is like invisible conductive film, almost entirely see-through yet still carrying electricity. The vast surface area and exposed p-electron cloud of graphene allow facile chemical modification and adsorption of molecules. Functional groups or receptor molecules can be tethered to graphene's surface without significantly degrading its electronic properties. Adsorption of target analytes induces detectable changes in graphene's electrical resistance, enabling ultra-sensitive detection down to single molecule levels. This capability underpins graphene-based gas sensors, biosensors, and environmental monitors. Graphene chemiresistors detect trace ammonia gas concentrations at parts per billion levels. Graphene is like a nanoscale sticky pad that changes its electrical fingerprint when it picks up even the tiniest particle. Dispersing graphene within polymers, metals, or ceramics dramatically enhances composite mechanical, thermal, and electrical performance at minimal loading, less than 1%. The strong interfacial bonding and large aspect ratio of graphene platelets transfer stress efficiently and create conductive networks. These composites combine lightweight form factors with multifunctionality, enabling structural health monitoring and self-sensing capabilities. As a result, graphene-reinforced composites are poised for high-performance automotive, aerospace, and sporting goods applications. Graphene-infused epoxy composites produce airplane components that are both stronger and electrically conductive for de-icing. Adding graphene to plastic is like mixing steel fibers into concrete. It transforms a weak material into a super strong, multifunctional composite. Graphene's high surface area, conductivity, and chemical stability make it an ideal electrode material for batteries and supercapacitors. In lithium-ion batteries, graphene coatings facilitate rapid charge transfer and accommodate volume changes, improving cycle life and rate capability. Graphene-based supercapacitors deliver ultra-fast charge/discharge cycles with energy densities surpassing conventional capacitors. Integration into photovoltaic cells and fuel cells enhances charge collection and catalytic activity, boosting overall energy conversion efficiency. Graphene-enhanced supercapacitors charge to full capacity in seconds while delivering high power output. Graphene in batteries is like turbocharging a car's fuel system, delivering energy quickly, reliably, and repeatedly. Biocompatible graphene derivatives serve as scaffolds for tissue engineering, drug delivery vehicles, and antimicrobial coatings owing to tunable surface chemistry and mechanical strength. Graphene oxide membranes exhibit selective permeability at the molecular scale, enabling desalination, water purification, and gas separation with unprecedented efficiency. Their antibacterial properties further ensure sterile filtration without chemical additives. These biomedical and environmental applications illustrate graphene's transformative potential in health and sustainability. Graphene oxide filters desalinate seawater by rejecting salt ions while allowing water molecules to pass. Graphene membranes act like superfine sieves, letting water flow freely while blocking impurities at the molecular level.